Okay, so let's get started. So today's topic is going to be on distributed file system. A couple of slides remaining from the web case study that I had done 2 weeks ago. I will come back to it later. Okay, so I want to do the distributed file systems topic today, and then we'll come back. So today I'm going to talk about file systems and what distributed file systems do, and provide some case studies to give you a flavor of how different systems out there have actually made several design decisions with respect to their structure, consistency, caching, replication, and so on. So, two high-level concepts are how distributed file systems work and what assumptions the servers make. So, first of all, you have to understand what a distributed file system is. Okay, so any file system that allows a machine to access files stored on another machine is referred to as a distributed file system. Typically, if you have your own laptop, you are accessing a local file system. Those are files on your disk. Okay? If there's any way to access files over a network, okay, whether it's using Windows or Mac or Linux, to a variety of different file systems, you have a distributed file system. Okay? So in this case, there's a server which stores files and there's a client that accesses files. Okay? There are two canonical models for distributed file system. One is referred to as a remote access model. The another one is referred to as an upload-download model. Okay? In a remote access model, anytime a client wants to access files that are stored on a server, it just sends requests to read, write, open files, close files. All of those requests are processed at the server and results are sent. So if you say read some number of bytes from a file, you send that request and the results come back. Okay, so all of the processing is done by the server. The work is done by the server. In the upload-download model, whenever the client opens a file, a copy of that file is transferred to the client. Okay. Once this is done, all accesses to the file are local, okay, because all reads, writes are actually done on the local copy as is shown here. And then once the file is closed, the results are sent back to the server. Okay, so there's a old version of the file. Once you bring the version over, and then the new version is sent back. This is referred to as the upload-download model. Okay. So two different models. The remote access model, as we'll see, can be stateless. The upload-download model, we'll see, has to be stateful. Why will become clear soon. The consistency issues are simpler to handle in the remote access model. They're somewhat harder to deal with in the upload-download model, because generally the assumption is there will be many clients, not just one for this file server. So if another client opens that same file, okay, you have an old copy here because there's another copy that's sitting with the client, and if there are multiple such copies, how to keep them consistent becomes more of a challenging task. In this case, all the requests are handled by the server, so consistency is handled at the server level. So it's somewhat more straightforward. Yeah. So these are the two high-level models for designing a distributed file system. Okay. The other dimension that we'll keep an eye on as we do the case studies are whether the server is stateless or stateful. In stateless server, no real information is kept about which are the clients accessing the files on the server, which files are open, and so on. So really, all the state is maintained at the client end itself. The server is stateless. Okay? When you say when you look at stateful server, the opposite is true. The server maintains states about which clients have accessed what files, which files are open, and so on. This is very similar to what we had looked at in the web server context. So there are these two scenarios, and again, there are issues with respect to consistency, reliability, etc., that are best studied in the context of various case studies. So keep these two things in mind. What is the high-level structure, the upload-download model or remote access, and whether the server is stateful or stateless. Okay. With that very brief description, let's start actually looking at real distributed file systems out there. We'll start with NFS. This is the most common NFS stands for network file system. Okay, so it's the most common file system that's out there in the Linux world. If you have any form of Linux, Unix, BSD, any of these protocols, operating system, they support the NFS protocol. This allows you to take files that are stored on a server and share it with clients. Okay. What's shown here is a picture with one server and one client. So there can be an arbitrary number of clients accessing each server, but we only show one. So there are files stored on the disk at the server. They can be accessed by a client here. Typically, when a client accesses a file, okay, this is sort of the OS level structure that is being shown here. Okay, depending on whether you access local files or remote files, your OS is going to process the request through one of two paths. Okay? If it's a local file, then you basically have system calls that go to this layer called the virtual file system or the VFS layer. And if it finds that it's a local file, it just sends it to the local file system, which accesses the local disks and returns whatever results are requested. If it happens to be a remote file, in this case an NFS file, that request is sent to the NFS client code in the kernel, in the OS kernel. The NFS client code makes an RPC request to the server code. Okay. The server code then hands it to the local file system for processing. The local file system will retrieve whatever files are being requested or parts of the file or whatever, and then the RPC returns back to the client side, and then it's handed back to that. Okay. That's the two paths that your requests are going to follow, whether it's a local file system access or remote file system. NFS, as I just mentioned, uses RPCs. Okay? In fact, when I talked about RPCs early on, I mentioned that RPCs were actually implemented by the Sun OS when they implemented the very first version of NFS. Okay? This is how RPCs actually became popular. Sun implemented RPC layer and then implemented the first implementation of NFS on top of that RPC. And since then, RPCs have of course been used for lots of other things. Is this clear? Okay. So this is a table that shows various NFS RPC calls. This is essentially the NFS interface that is exported by the server to the client. Okay, we don't have to go through every single call here. There are only two things that we want to look at. There are these two columns here which show NFS version 3 and version 4. Okay, these are the two versions of NFS that are still in use today. Okay, version 4 is the later version, obviously, and version 3 is still quite popular. But there's a key difference between these two, and that's the reason we have them up there. Until NFS version 3, NFS had made a design decision to keep the server stateless. No state was ever maintained at the server. Starting with NFS version 4, servers can be stateful. Servers are allowed to keep state. And we'll see what implication this has on how you design NFS, okay, or distributed file system. Okay, it's an important distinction. So that's the thing to keep in mind. Now, I'll just give one example of what it means to be stateful or stateful. Okay, so just look at this row here, which stands for the open call. Open allows you to open a file, to read or write. Okay, that's a system call that translates directly to this NFS call called open. Okay, so whenever you want to start accessing the file, you open it and then access. So what you will see is NFS version 3, there was no such call at all. Okay, so by no, that means this call was not present. Starting NFS version 4, this call is now actually part of the NFS spec. Okay. So you can ask the question why. Now, typically what happens on a local file system when you open a file is that the kernel will open the file for you and it will maintain some state in the OS kernel saying this process has opened this file and so on and so forth. And so state of the file is actually meant that the file is open and the file descriptor, all of that is actually kept by the OS kernel. Now, if NFS is a stateless, NFS version 3 is a stateless protocol, the OS on the server side cannot keep any such state as per NFS. Okay, so you cannot. So that's the reason they said there's no point having the open call. Okay? Applications will still have to open the file, but as far as NFS is concerned, it doesn't do anything. All it can do is to check whether you have permissions to access the file, but no state is maintained. And this is why this call was not even supported here. But starting NFS version 4, because it's stateful, that call is supported and it provides the normal semantics. And I'll show you some figures on the next slide which actually show what is happening. So I'll not go into details of all these operations. I just wanted to point one. But let us look at now the process of opening a file and reading some data from that file. Okay? So as far as the application is concerned, it is going to say open a file, putting all of the arguments, and then you'll say read some data from the file. Okay? And you can use C or Java. In Java, you will basically use the Java interface to open the file. But underneath, all of these libraries or JVM are going to make the system calls to the host. This happens to be an NFS call, and this is what is going to be the interactions between the NFS client and the NFS server. Okay. Open is basically going to translate into a lookup. Okay. All that the NFS client will ask the server is, does this file actually exist, the one that the user wants to open, and does the user have permissions to access the file? That's all you're going to do. Okay. So you're going to look up the name, okay, because if you're trying to open a file that is not valid, okay, then you have to do certain things. Either you have to say create the file, or you are basically going to say the file doesn't exist if you're opening it. Okay, and then once you issue the read, then you're going to actually read the data. Because the server is stateless, every operation that the client does on the server has to have a complete request saying this is the name of the client, this is the file that we are trying to access, this is what we are trying to do on the file. Okay? Every request has to have all of the information needed by the server to process it, because any previous requests made by the client are not stored at the server. Server is not stateful. It doesn't know that the client has this file open. So every time you actually issue reads or write, you are actually going to have to do all of these operations. Now, if you actually had a stateful server, you would just open the file, and the server would keep track of the state of keep track of the fact that the client has opened the file. So subsequently, you don't have to provide lots of additional information. You can just provide, in Unix, for instance, you provide the file descriptor, for instance. In C library, you provide the file pointer. So you're just going to provide that, and that allows you to access the file. So NFS version 4 just basically is going to look up, open, and read, which is different. So you'll see that the open call doesn't actually is not present in NFS version 3 because it was a stateless protocol. But starting version 4, you do have it. We'll see what are the implications of all of this in just a moment. This is just to show you two things. One is that how version 3 behaves in version 4. That's one thing. The other thing that version 4 has introduced is this notion of compound RPCs. Okay? That basically allows you to piggyback multiple RPC requests in one call or one packet. Okay? So you will see that open, lookup, open, and read are 3 separate RPC requests. They have been sent as one message, or what is referred as a compound RPC, to the server. So the server gets 3 requests piggybacked as one request. And then it will perform all 3 operations and send back a result. So you can ask, why do you need compound RPCs? Why do you not want separate RPCs? Why can you not do separate RPCs as was done before?
You still can, but it's faster this way. Right? You don't have to run.
So you can of course do this, but this is clearly faster because it reduces the round trip time. Rather than making 3 requests and having 3 round trips, you make 1 request and get back 1 reply. Okay, that's just a performance optimization. It's just reducing the number of messages that are going back and forth and the latency to process these. So version 4 has this notion of compound RPCs, multiple operations supported in a single call. Okay, that's a performance optimization. Okay. So this slide is showing how clients can access files stored at the server. NFS has this notion of a mount protocol. Mount protocol allows you to establish a connection with the server and access some file or some part of the subtree that is stored at the server. Okay, so it basically shows you the server that has exported a certain part of its subtree. In this case, these are user home directories. Okay, so it's assumed that home directories are stored on the server, and any client can essentially run the mount protocol to access it. So what happens when you run the mount protocol is you establish a mapping between certain parts of the subtree stored on the server to the client. Okay, so in this case, this is the subdirectory of this user and all the files that are stored in that home directory. These are mapped onto this client machine under this part of the local subtree. So at this point, when you say /remote/vu/user, you are basically accessing files that are stored on the server. This allows you to create a mapping. Okay? In Windows, this is equivalent of creating a network drive. If you have actually used Windows, you know how to create new network drives, where you can create F drive and E drive and so on. That's the same kind of protocol that's being used in the Windows world, that you construct this mapping, and from that point on, you can just simply CD into that drive or CD into that directory and access it as if the files are local. So the mount protocol is a way of establishing a connection with the server and taking a part of the subtree that the server has exported and mapping it to the local file hierarchy. Okay, so this is how you basically access files that are stored on the server. Now there are some interesting questions that arise when you try to use the mount protocol. Okay, the first one that we are going to look at is the notion of transitivity. Should mount protocols be transitive or not? And what I mean by that is the following. Let's assume there is this server B here, and that has exported this part, these files to another machine. Here is server A that has mapped these files onto its local subtree here. Okay. So now this server can actually access those files using these paths, /packages /draw, for instance. Okay. Now what the server itself has exported something that includes this mapping to other clients. Okay. And here's a client that has taken all of these application packages here and mounted them here. Okay. Now the question is, if this client tries to access something that is basically here, which is stored on this server, should it be directly allowed to access it or not? Is that clear what the question is? Okay. Server B exported some files which are mounted by server A. Server A mounted some files in the subtree that includes the mounted files from B. Okay. And a client has mounted all of those files. Now, can client then directly access data from server B? Or should it be allowed to access clients files from server B or not? The question's clear? So as it turns out, NFS does not allow transitive mounts. Right? If one machine mounts files from another machine and exports some other files, you do not get access to the first machine's files directly. Right? Because that's a security risk. Typically, when server B has exported these files to A, it's telling server A that you can access my files. If server A then goes and exports some other files, this client doesn't get access to server's B file because server B has to explicitly export them to this client, not transitively export them via another server. Okay. So if the client actually wants to access these files, it has to actually set up a separate mount. That is what is shown here. Okay. So it is going to mount these files from server A and these other files from server B. Okay, is that clear? So for security reasons, transitive mounts or recursive mounts are not allowed, because that basically breaks the security trust. Because if A trusts B and B then goes and re-exports something, you don't know who it has re-exported to. So you don't actually allow somebody else to come start accessing your files. So that's basically a design decision that NFS has made. This is a security policy that NFS supports. Okay. And the last point about mounting is this notion of auto-mounting or mount on demand. Okay, what mount on demand says is that rather than establishing the mount mappings at boot time, okay, typically the way mount protocol works is there's a file that you specify all the mount mappings. And then within this file, you specify that these directories you mount from these machines, and then when you boot up, you establish those mappings and you're done. Auto mounting, what it allows you to do is it doesn't actually require you to do this at boot time. It does this on demand. When you CD into a directory, if the directory happens to be an NFS mount, it will automatically mount it on the fly. So in this case, it shows that when this user Alice logs into her machine, client machine, our home directory is auto-mounted from the server. This mount protocol is run on the fly when she logs in rather than when the machine boots up. Okay, so, and then once she logs out, the mount mapping is dissolved. Okay, so this allows you to set these up dynamically. Okay. I'm just going to show, for those of you who have used the EdLab, you can actually see all of this. Okay, so I'll just... access the machine, you can see it. network. Sorry?
Do you want to show the file?
Yeah, I'm trying to see if the file is there first. But, okay, so you can actually do df and see that these are the mappings. So you will see in this case that this is the name of the server, that's the mount point, and this is where it has been mounted. So these are all the NFS mounts that have been established when the server booted up. Okay, so you will see there are lots of them, and some of them are local. So here is a remote one. So that's the name of a machine. These are all the Linux RPM packages. Okay, that's basically stored on this machine, and these are mounted on this local machine. Okay, so now you can access files stored on. So all of these mappings are actually provided in a file. So when the server boots up in a config file, when the server boots up, all of those mappings are established. And now you can actually just do cd into this directory, okay, and you can access files that are stored on this machine as if they're local files. So that's basically the abstraction that NFS gives you. Very similar to any network file system abstraction. Okay, so I will show you Automounting maybe another time, because I'm not sure that machine there had actually configured it. Okay. Now that's security policy. Now we'll talk a little bit about consistency and caching and so on. Okay. So to understand how consistency works, we have to understand the semantics that the file system provides. So any local file system on any Unix-like machine provides what are called Unix semantics. Okay. In Unix semantics, what this says is any operation on the file is instantly visible to any other processes that access that file. Okay, if process A writes to a file and process B reads that file locally on that machine, any write that has actually just been performed is immediately visible. That's what you expect. If you write to a file and some other process reads it, you expect whatever was written to be visible. NFS actually does not provide that semantics. NFS provides weaker semantics because of consistency reasons. So in NFS, a process on one machine can write to a file. Okay? If a process on another machine reads that file just after that write, it is not guaranteed that those writes will be visible. Okay? The reason for this is, as soon as you write to a file, those changes are not immediately sent to the server. They may be cached locally. Okay? So consistency is weaker. If they're cached locally, the server doesn't even know that this write has been performed. So if another process on a second machine reads the file, the server still has the old copy of the file. So it is actually going to provide you the old version of the file. Okay? As a result, you do not get Unix semantics. And strange things can happen because of this. So for instance, you may actually have, let's say, some source code that you're writing. You open it on an editor on machine A, and then you make a one-line change and you save, let's say. Okay? And then maybe you use a second machine to build the code. Okay? And then you type make or whatever build program you use. It's not guaranteed that any changes you made are actually already made it to the server. So the server may not have even seen that update, so your make may actually produce incorrect results. So these kinds of problems can actually exist with NFS because changes are not immediately visible to other machines. This is because of consistency reasons, and I'll show you what consistency meant. So you have to keep these issues in mind. If you had strong consistency, this would not have been a problem. But NFS does not provide you that strong consistency. It will be much weaker consistency. Okay. In fact, what NFS actually does is very simple money implementation. So the protocol does not specify any consistency requirements. It leaves it to the implementation. What most implementations do is every 30 seconds, every half a minute, they simply flush whatever has been written to the server. Okay. So if you write to a file that is on an NFS server, it may take up to 30 seconds before your OS, local OS, actually sends that write over to the server. Okay, because those files that write may be cached locally and sent up to 30 seconds later. And because of this, consistency is much weaker. It may take up to 30 seconds before other machines are going to see that this file has been written. And this 30 second is an implementation decision. There's nothing in the NFS protocol that says it should be every 30 seconds. Okay. Now, another issue with respect to NFS is the notion of file locking. Now, most operating systems, in addition to opening a file and reading and writing files, also allow you to hold a lock on the file. You can hold a read lock or a write lock. If you hold a write lock, then you're excluding other processes from writing. Now, locking is typically, if you have written applications, you'll only use locking if you have multiple processes trying to read or write to the same file at the same time. The most common scenario for locking is for email, to provide consistency. So your inbox, which is where new mail arrives, is typically a file, or it could be a set of files, but let's assume it's a single file. There's the mail server that's delivering new mail as it arrives into your inbox. It's simply appending that new email to your inbox. And you have a mail client that's trying to read that data. It could be an IMAP client or it could be a local client, it doesn't matter. For consistency reasons, mail uses file locking. Because what you don't want is your mail client is trying to do something to your inbox while new mail arrives. That means your inbox is a shared data structure, it needs to be locked. You may start deleting some mail from your inbox and new mail can arrive. If you try to read or write at the same time, your mailbox will get corrupted. So for this reason, you need file locking. So what would happen is typically either the mail server will try to grab a lock on the file so it can get exclusive access, or your mail client will try to grab a lock on the file so it gets exclusive access, but not both. Okay, so your file system for mail to work correctly must support file locking. Now, since NFS version 3, version 1, 2, and 3 were stateless, there was no notion of file locking at all. File locking inherently assumes you have to have state. You need to know who is holding the lock. That is state. If the protocol is stateless, you cannot keep any state. If you cannot keep state, you don't know who holds the lock on the file. Because the file locking was not supported until version 3. Version 4 has, since it's stateful, actually supports locking. Okay, so what is shown in the table here are NFS calls that allow you to lock a file. So here it says lock a file, or basically you can lock a range of bytes. You don't have to lock the whole file. You can say lock bytes offset X to Y. You can lock a part of the file, you can lock the whole file, and so on. You can release locks and so on and so on. But that was supported only version 4 and onwards. Until version 3, you did not have this. This is why if you actually read administrator manuals, they will say do not run email over NFS. If you have a mail client that is running on the machine, it will say do not access a mail spool that's run on an NFS server, because chances of corrupting your inbox are very high because there is no locking. So if you read any documentation on Linux or whatever, it says if you're running version 3 and you're running email or version 3, don't run NFS, don't run mail clients on an NFS client machine, because locking is not supported. It will corrupt your inbox. Okay, that's the reason, because it was stateless. So these are all implications of design decision. You cannot have mail running correctly on version 3. You can only do this if all the clients and the server run only on the server side. With IMAP, that's okay, because the IMAP server is on the server machine and so is the mail server. And locally, the server can support locking, but not over NFS. Okay. So those are some design decisions that they made, but as of version 4, all of that has been addressed because it's stateful. Now, as I mentioned this notion of caching, where NFS supports weaker semantics. Okay, so here is a figure that shows you what is happening. So this is the server, this is the client, and there is an application that's accessing it, and there is a cache. All writes are written to the local cache, and every 30 seconds they are flushed over to the server, as per most implementation. So any writes that you do to NFS file are not going to be seen by the server for up to 30 seconds. Okay, so if the second machine accesses the file at the same time, it could potentially see a stale version of the file, an older version of the file, okay, because you are not guaranteed that changes will be immediately visible. You can actually test this on most machines. So you can, for instance, go to the EdLab. You can log on to 2 EdLab client machines, okay, and open an existing file and write to it, okay, and then just cat that file on the second machine, and many times, not always, but many times you'll see that the writes you have made are not visible. But you do this a few times, in a few seconds you see that the write becomes visible. So that's all a reason, that's all an artifact of having weaker consistency. Now, starting version 4, you have more interesting optimization. Okay, so NFS by default supports the remote server model. Okay, clients send all the requests to the server, they're performed at the server, and results come back. Okay. But starting version 4, you also have the upload-download model that I presented on the very first slide. This is implemented through this notion of delegation. Okay, so here is what happens. So let's say this is the server, that's the client, there's a file stored at the server. The client opens that file for reading. Okay. If this is the only client that has currently opened the file for reading, what the server does is it delegates responsibility for the file to the client. Okay. What we mean by delegate is a copy of that file is sent over. And the server says, now you take over the file, you have the master copy. Okay. So now all subsequent changes can be done locally. You don't have to make RPC requests to the server because the master copy is with you. Okay, so you can do all of the reads and writes locally and then send back the file once you are done. This is simply a performance optimization. The local reads and writes are going to be faster than remote reads and writes. Okay, so if you have the master copy here, all the updates can be done locally and later on you can send the file back. Okay, this is basically the upload-download model that I was talking about. Okay. Now, although the server can delegate a file, if it detects that multiple client machines have interest in the file, it can recall the delegation. It can say that you are no longer the master, send me the master copy back. So I am going to revert back to the remote access model because multiple machines are interested, so they will all make RPC requests to the server, that's me. And I will deal with all the reads and writes at my end. So client delegation works, the file delegation works well in cases where there's only one machine interested in a file at any given time, which for a majority of instances is fine. Okay, typically, if you have the home directory stored on the server, typically only you will be accessing files in your home directory, not other users. Okay, each user has his or her own home directory and they can access them directly. But in scenarios where there are multiple machines accessing the file, the same file, you can actually revert or recall the delegation and so on. So version 4 supports both the remote access model as well as the upload-download model, which is an interesting optimization they put in here. Yeah.
So I wonder which version of NFS is capable of handling more clients, because it seems that when you use delegation, then you don't have to process all the reads and writes. So you're technically able to deal with more clients. And on the other hand, since you're stateful, yes, then
so that's a very good observation. The question is, how does the fact that you can do delegation impact scalability? On the one hand, if you start offloading a lot of responsibilities to the client, saying you deal with file A, you deal with file B, you deal with file C, lots of the accesses are local, so there's less load on the server. So you can scale more. But at the same time, because the server has to be stateful, because it needs to know that it has offloaded file A to machine A and B to another machine and so on. So being stateful reduces scalability. And so that results in, actually it's a very interesting trade-off where delegation is put in for performance reason, but the fact that you're stateful also hurts performance and scalability. Right? So, but that's not the only problem. Version 4 is also more complicated. It has a lot more additional features, so it has added complexity. There is more code. So version 4 was less scalable, not because of this optimization, but simply because they added a lot more features that added complexity to the server. Okay, this is why by default when you set up NFS, it's still version 3, okay, not version 4. Version 4 is supported, but I think they're still trying to optimize the code so it performs as well and you can actually take benefit of the feature rather than all of the features being a disadvantage, because the code has become larger and more bloated. But from a design standpoint, it's an interesting question to ask. Does the fact that you are delegating responsibility help you or hurt you? Because it helps you in that others do more work. It hurts you in that you have to keep track of more state. Okay, so at some level, there is going to be an inversion. If there are lots of delegation, the state you maintain is going to actually hurt. Any other questions on this? Okay. So very last point we'll talk about is this notion of RPCs failing and how NFS actually handles this. Okay. Original version of NFS ran on UDP. Okay. Today NFS by default runs on TCP, so packets getting lost are handled at the TCP level. Okay. The NFS layer doesn't actually have to deal with it. Okay. But you can still run NFS or UDP, and back in the days where UDP was the only protocol, not TCP, you have to deal with, you make an RPC request to the server, you never hear anything back. What should you do? Okay, so this is a scenario that's actually shown. So a client issues an RPC request. Let's say it says write 1 byte to this file, and that goes to the server. Response doesn't come back. Okay, so that's a timeout, and you reissue the write, saying write 1 byte to the server. Now, as you can imagine, these operations have to be idempotent. Okay, if you say write 1 byte to the server and you write the byte twice, or append the byte twice, you will actually get a file that has twice the data that you intended to write. Because you can't have the operation being done twice in some cases. Or let's say you say delete this file. Okay, the first time you delete it, second time you say delete the file, you will get an error because the file no longer exists. So you want all operations to be idempotent, which means that if you do it any number of times, the result should be the same. The way this is actually handled by the server is by maintaining a log of all the requests that have actually been processed. Okay, so it's a cache of the request. So every RPC request comes with what's called a transaction ID. That's a request ID. Okay, it's an integer. Let's say this is a unique request number. Server keeps track of which requests have actually been processed already. So if there's a timeout and the same RPC request is actually issued again, the first thing that the server is going to do is just check the log, saying, have I already processed this request? If I process the request, I'm not going to reprocess it. I'm just going to look at the cache and see the output of the RPC and just send that RPC result rather than reprocessing it. Okay. This is how you're going to get idempotent operations. If the same request is issued twice, if you have actually successfully received it the first time, you will not reprocess it again. You will actually look at the cache, find the reply, and send the reply. If on the other hand, that first request was actually lost by the network, then only the second request will make it through and you will actually process it. Okay, so it doesn't matter how many times you issue the RPC call, it will be processed exactly once. Okay? So this is sort of giving you exactly one semantics. If you remember the RPC discussion, at least once, at most once. If you do at least once, you're going to be in trouble. If you process the same RPC multiple times, you may get undesirable results. So you want exactly one semantics. Okay, so and that is basically handled by this notion of having a cache of processed RPC calls already with the reply stored in the cache. Okay. So as you can see in the plugin, this is basically the end of the discussion on NFS. So you will see there are many design decisions about whether the client is stateful, the server is stateful or stateless, security policies, failures, how they are handled, how caching is handled. And so this case study should give you some flavor of how all of the topics that we had studied back sort of in the earlier lectures are having an impact on real design decisions that have been made, in this case for file system design. Okay. Okay. So the remaining time I'm going to talk about two additional file systems. One is called Coda and the other one is XFS. And the reason for having these two is to just see some other distributed file systems out there and see how they differ from NFS. And you'll see that there are some interesting differences between both Coda and XFS from NFS. So Coda is actually a name of a research project that was done at CMU back in the late 80s and the early 90s. Okay. Eventually, the Coda file system did become commercialized. There was a predecessor to Coda called the Andrew file system. So some of these ideas have become commercialized. Some of this code actually made its way into Linux and so on. But these are the Coda at least is not a widely used file system as NFS. NFS is very widely used. It's seen practically in every environment that has any Unix or Linux machines. You'll see NFS being used. The Coda is actually used in very selective cases, but it had some interesting ideas, and this is why we want to look at it. So the main thing to keep in mind is Coda is a distributed file system designed for mobile clients in mind. NFS is a distributed or a network file system designed for wired clients. It's assuming that the client machines are connected over Ethernet or some wired connection to the server. Okay? Coda assumes that you have mobile clients. Okay? So you can ask, so what does it matter? How does the fact that you are mobile change the design of the file system? What is different if your clients are mobile versus they are wired? So what do you think are the difference between wired clients and mobile clients? Then once you understand that, you will see what the file system has to do to deal with those differences. So if you are a file system and you are dealing with mobile clients, what would be different from having a client, a machine that's wired and has an Ethernet connection to the server? Dropped connections. Why are connections being dropped? So mobile clients essentially imply that machines move. Your laptop is connected to the network here. You shut it down. Maybe you go home. You connect to your home Wi-Fi. Okay. So what has happened in the meantime? While your machine was shut down, it was disconnected from the network. It was not connected. When it came back up again, it has a different IP address. Okay. So as machines move, they'll get disconnected and they'll reconnect, but possibly with a different IP address. But this has interesting implications on what the file system has to do. Okay. So basically you handle sort of this notion of being disconnected from the network. Okay. There are other scenarios. Let's say you take your laptop and go on an airplane. Okay. And you start working on something on the airplane. You are working on your machine, but you are not connected to the network. Okay. So what should the file system do to help you? Okay. Typically, if you are disconnected from the server, the default assumption is you cannot access files on the server anymore. Right? And if you are not connected, how can you access files? So what Coda does is it allows you to keep a copy of the files that are on the server on your local machine in a cache. So you can work on your files in what is called disconnected mode. Okay, the simple idea in Coda is machines can get disconnected, but you want users to be able to access their data even if they're disconnected. Okay? And the way you do that is your client operating system will transparently keep a copy of your files on the server. This is completely transparent to you. So even though you may not be connected, you have no network access whatsoever, you can still access your files. Okay? That's basically copies of your file on the server. And when you reconnect, any changes you have made locally will be sent to the server, and every changes that were made on the server by other users are sent to you. You will have this resynchronization protocol. Okay. So if you have actually used Gmail, which I presume most of you have, Gmail has now a notion called disconnected mode. Okay. This is essentially what Gmail disconnected mode does, because Gmail essentially is a web mail, and you can only access your mail if you are connected to the network. Okay? The big disadvantage in Gmail is if you are now in an environment where you have no network access, you can't get your email anymore. You can't do anything. Okay? In disconnected mode, actually you keep a cache of the mail that the server has on your browser cache. Okay? So you can continue to access your Gmail even if you are disconnected, and you can work on your mail, and then when you later you reconnect, it resynchronizes. Okay, so these are ideas that originated in Coda 15-20 years ago that are appearing in other systems. In this case, Gmail is disconnected. Okay. That's the basic idea. Okay. Also, there are lots of issues here to sort of work with them. So basically it says, so the basic assumption is that the network can get partitioned. Machines can disconnect from the network, but you still want the ability to access it. The way you do this is replication. You keep a cache, you replicate the files on the cache, and then you basically allow the users to access the file. But the important design decision that this file system has to make is what files to cache on this machine. Okay? You can't take all the files on the server and keep them local. The whole point of having the server is lost because the assumption is server has a lot more disk space than your client. Okay? If you take every file on the server and put it here, you don't need the server probably to begin. Okay? So you need to be able to cache a subset of the files. So the file system has to guess what files are you interested in. Okay? Typically it may be your home directory, could be your inbox. So it will guess based on what you've accessed previously. Okay? Based on your history, it will guess saying these are files that this user is most interested in, so I'm going to keep a cache of those files on the client. Okay, so if you get disconnected, those files are still available. Other files, you are out of luck. Okay, it doesn't mean that every file is accessible. The most commonly accessed file by a user are accessible in cache. Okay. And when you reconnect, you are going to basically have a resynchronization protocol, which allows you to compare every file with the server to see which files have changed and then synchronize them. Okay, typically this is done by keeping what is called a version vector. Okay, version vector is simply every time you update a file, you have to increment the version vector. Okay? So the client will keep its copy of the version vector, the server will keep its copy of the version vector. Okay, so whenever you reconnect, you compare. The version vector has not changed, that means the file was not returned to at the client or the server, it's the same file, so there is nothing to do. Okay? The server has a newer version, then somebody wrote to the file at the server, so you bring that file over. The client has a newer version vector. Okay? Then you say basically this client wrote to the file, the user at the client has written, you send it over. Okay? And you can also have write-write conflicts where the user updated the file and some other user updated the same file at the server. That's a write-write conflict. If you have a write-write conflict, Coda says, I don't know how to resolve this. You'll just tell the user saying, look, there is a problem, you figure it out. Okay? Exactly what happens in source code control. If two users update the same source code, you'll get a conflict. If you use the SVN or Git or any such thing, you know what write-write conflicts are. Okay? So in those cases, you have to tell the user saying, this file was written by multiple users or modified by multiple users. You have to manually resolve this conflict. The system doesn't know what to do. Same ideas. So many of these ideas originated here because of this notion of being disconnected and so on. Okay. So this is basically a state transition diagram of how the client works. Okay. At any point, the client could be in one of three states. One is called holding, emulation, and reintegration. Right. In the holding state, you are connected to the network and are actively downloading files that you want to cache. It's called holding. You keep a hold of files on your machine. Okay? So you are connected and you are saying, let me, before the machine disconnect, let me try to opportunistically bring whatever files the user is interested in and keep a cache on the local machine. Once you get disconnected, you go into emulation state. Okay? In the emulation state, the file system pretends that you are connected. So everything looks normal. You have no network connection. But file system behaves as if you are connected, all your files are accessible, so it's completely transparent. So you're emulating the fact that you are connected, although you are not. Okay? So you can continue to work on your file, nothing seems to have changed at all. Okay? Once you reconnect, once you actually go back and connect to the network, you go into reintegration. In reintegration mode, the client file system and the server file system start comparing notes, saying what has changed at which end, and they try to resynchronize. Okay. Once resynchronization is complete, you go back into holding mode, saying, okay, I have resynchronized, are there any other files I should bring over, etc. So you'll be in one of these three modes, holding, emulation, or reintegration. Okay. That's basically how Coda is actually going to work. Okay. So the big idea that this file system introduced was this notion of disconnected mode operation, how to make sure that users can access their data even if they're not connected to the network. Okay, and this was back in the 90s when laptops were just appearing on the horizon. So this was actually a file system that was futuristic looking. So at that point they thought about this problem, saying laptops may people walk in and out of networks, so they still need access to this data. So today these ideas are present in many other systems, such as Gmail disconnected mode, source code control system. They all use some of these ideas in some shape or form. But Coda was actually the file system that introduced some of these ideas. So it's an interesting file system to look at because it's designed for mobile access. Okay? And this mobile access ideas were thought of in the 90s, which is almost 20 years ago, and not today, which is almost a common case scenario. Okay? So that's Coda. Any questions on this? There's a quick overview of Coda. Of course, there are a lot more details that I glossed over, but these are the high level points. So last file system I'm going to talk about is called XFS. There are three interesting points here. The first one is XFS is what is called a serverless file system. So it's almost a P2P like file system, not quite a peer-to-peer file system. It's almost a P2P type file system where there's a pool of machines and any machine can become a server for any file. In most distributed file systems, there's a designated server or a designated set of servers. Okay? In XFS, the choice of who is the server for what file is dynamic. You can say this machine is the server for this file, this other machine is the server for this file. So effectively, it's serverless in that any machine can become a server for any file, and any machine can become a client for any other files. Sort of like a P2P file system, but it doesn't use P2P protocol. It's actually Unix like. That's the first difference between XFS and NFS and Coda. Okay, in NFS and Coda, there are clients and there are servers. Okay, they are distinct entities. In XFS, the entities are mixed up. You can be a server for some files and client for some other files. Okay? That's the first thing. The second interesting point that XFS uses is this. It uses this notion of RAID, which is a redundant array of independent disks. So what this allows you to do is it takes disks on multiple machines or even multiple disks on the same machine, and it allows you to spread the data from your file systems on multiple disks. And we'll see what important implications this has. The third thing that it does is basically it uses log structured organization, which I'm going to only talk about very briefly. So I'm going to focus most of our effort on RAID, or not effort, but most of the discussion on RAID here. Okay, so let's talk a little bit about RAID. There's a picture here. So the notion of RAID assumes that you have, let's say, either a single machine or more than one machine that have multiple disks. Okay? And you want to collectively use the data on this storage space on these multiple disks to store your files. Okay? Now, in Coda and NFS, we assume that the server stored all of its files on a single disk. Here we are going to relax that assumption. We are going to say that data can now be stored on multiple disks. So how do you make this happen? So you could do the simple thing, which is say some files are stored on disk 1 and some files are stored on disk 2 and some files are stored on disk 3, and this is how I partition all the files in my file system across multiple disks. That's the straightforward thing. You say all files in this directory or its subdirectories go on this machine or this disk. This directories and sub-disk go on this machine, this disk and so on. This is called a partitioning approach. Okay? So you could do that, and that basically allows you to take the notion of a single disk and extend it to multiple disks. The problem with partitioning is that you do not know a priori how much storage space will be needed by each directory and where the accesses are going to be. It may be that the directory you put on this disk, suddenly the user starts creating lots of files and you run out of disk space. And there may be idle disk space on these other two. Or files that are stored on this disk see heavy load, but these disks are not seeing any requests because all the users are accessing files stored on this disk. So if you use a partitioning based approach, you are going to get imbalances and skews. Okay? Because you do not know that. OS doesn't know a priori what the users are going to do, where they will create the files, which files are going to be get accessed and so on. Okay? So what's the other alternative to partition?
You could provide a sort of unified interface to access all the files, and the system will take care of where the files are.
Okay? So you can provide a uniform interface, and the system will take care of where the files are. That's true. Okay? But even if you provide a uniform interface, if you put the files on separate disks, you still have this problem. Right? Any other thoughts?
Divide a file into many pieces and store them in separate pieces.
Okay? So you could take a file, you could chop it up into pieces, and you can actually spread those pieces around. Okay? So if you actually do this, you have what is called file striping. Okay? And this is actually what is done in RAID and others. So if you don't know which files are going to be accessed on what disk, store every file, store parts of every file on all the disks. This will ensure uniformity. So what is done here is, let's say you have 3 disks and you have a file. Okay. A file is partitioned into blocks. You take the first block, you store it on disk 1. You take the second block, store it on disk 2. So take the third block, store it on disk 3. Take the fourth one, you put it on disk 1 and so on. So you've taken a block file, you partitioned it into smaller chunks, and you are putting these chunks on different disks in round robin fashion. This is called striping. So if you do this, every file is stored on every disk. Okay? So in this case, you no longer have to say, take this set of files, store it on disk, because you are basically chopping the file. Every file is going to be stored on all disks. This gives you several advantages. You get parallelism. Okay? So basically, if you now want to access this file, you send requests to different disks, so you get the throughput of n disks. Because all of these, each disk is independent, so you get n times speed up. Okay? So it's effectively you're getting parallelism by storing the file. If the entire file was stored on one disk, accessing the file would limit you to the speed of a single disk. The file is stored on n disks, you can send n requests in parallel to n disks and get n pieces of the files and then assemble it, and you get n times speed up. Okay, this is an advantage of doing striping. The other advantage is you get automatic load balancing. If some files are popular and other files are not, the load of the popular file still gets spread across all the disks, because the popular files are also spread on all disks, and so are all the unpopular files. If you had partitioned and some popular file landed on one disk and unpopular files on another disk, you'll get load imbalances. Some disks are more heavily loaded than others. Here all disks are equally loaded because all files are striped across all the disks. Okay? So this is referred to as disk striping, very important concept. We have just generalized a single disk file system into a multi-disk file system. Okay, so you have the ability to use storage space on multiple disks and have it pretend like it's one bigger logical disk. Okay, that's the advantage. Okay, but if you do this, there is one major disadvantage. Okay, the disadvantage is what will happen if there is a failure in the system. Okay, let's say this disk fails, which experiences a hardware failure. Okay, now all the data that was stored on this disk is gone. So what does that mean? Some parts of every file in your file system have lost data. In the partitioning case, if this disk failed, because you said some files are here and some files are only files that were stored on that disk disappear, only that data. But files that were stored on these other two disks are still available. Okay. In the striping case, if any disk fails, all of your data gets impacted, not some of the data. Okay. That's a major disadvantage of striping. And we are going to look at how you deal with this using RAID. So here is the main problem. Okay, if probability of a failure is P, and if there are n disks, the probability that any one disk will fail is 1 to 1 minus p to the power n. As n grows, this probability is going to tend to 1, which means that failures are going to become the common case. Okay? Put another way, this is another way to do the same calculation. Typical lifetime of a disk is 50,000 hours. That's many years. If you buy a disk, the vendors basically statistics show that typical disks fail after 5 years of normal use. 5-10 years of normal. Now, if you have a disk array with 70 disks, if you have this thing with 70 disks, basically the lifetime of any disk failing is dropped to 700 hours, which means basically it goes down from 6 years to a month. Because one of those, if you assume disk failures are independent, some disk is going to fail, and in about a month, at least one of your disk is going to go down, and then all your data becomes inaccessible. Okay, so you buy 70 disks, in 1 month, you lose all of your data. That doesn't sound too good. Right? So you need to basically add redundancy to sort of address this feature. Okay, so RAID is an acronym that stands for Redundant Array of Independent Disks. Okay? So you want to add redundancy so that if any of this disk fails, your data is still available. Okay, so RAID is a storage technology that allows you to do this. You can have RAID implementations in hardware or software. It doesn't matter, the concepts are still the same. Okay. So I'll talk a little bit about how RAIDs work. Okay. So there are different types of redundancy you can implement. Okay. Simplest form of redundancy is called mirroring or shadowing. Okay. As the name suggests, for every primary disk, there is a backup disk. Okay. So basically, your array is going to look like this. For every disk, there's a shadow disk or a separate second disk. So whatever is stored here is also stored on that other, is mirrored. Okay. So if one disk goes down, the other disk still has exact copy of whatever was stored there. So you can go to that disk and access it, so no data will be lost. Okay. This is referred to as RAID level 1. Okay. RAID level 0 means there is no redundancy, that is this. If some disk goes down, then your data is lost. So RAID 0 is no redundancy. RAID level 1 is mirroring. Okay. So mirroring basically says that you basically have a second disk for every primary disk in the system, and every time you write, you will send the write to both disks, so the disks are identical. They have identical contents. If one disk goes down, you have a backup disk. Okay. Now the disadvantage of this is it's going to double your hardware investments. You need twice as many disks to store a certain amount of data. Okay, so your disk costs have doubled. Okay, so you want a way to reduce those costs. Okay, so typically you will do more smarter redundancy than mirroring. Okay, so which is basically, so I'm going to basically jump. So there are RAID levels 2, 3, 4, which I'm going to ignore, go directly to RAID 5 and explain the concept. In RAID 5, what you use is you use some redundancy, but you don't use the same level of redundancy in mirroring. You use what are called parity blocks. Okay, so for if there are some number of blocks, D0, D1, D2, and D3 stored on these 4 disks, you take this block and you compute some extra information that is referred to as the parity block. This parity blocks allows you to reconstruct any data that may be lost if any of this disk fails. Okay. And the way you do parity is using simple XOR operation. So this is basically what is done. So you will basically take each of these blocks and you will XOR them. And then the result that you get is what is referred to as parity. So that's XOR of D0, D1, D2, and D3 is the parity that you are going to store them. And the way you reconstruct is if some disk fails, let's say if this disk fails, D0 can be reconstructed as D1 XOR D2 XOR D3 XOR D4, XOR P. That is a property of the XOR operation. I assume you know what XOR is. So XOR basically guarantees that if A XOR B equal to C, okay, then C XOR B is going to be A, or C XOR A is going to be B. Okay, that's what XOR allows you to do. Okay, and basically, so if you XOR any of these and you get P, you can basically, one of these fails, you can take the remainder and XOR them and reconstruct them. Okay. So now what you do is every time you write to a block, you will basically take all the other blocks in that group and you will construct an XOR and you will put it there. If any of this disk fails, then if a request comes to access that block, what the RAID system will do is it will recover, the retrieve all these other blocks, XOR them, and that will allow you to reconstruct this, or this, or this. Okay? So now your cost of redundancy has fallen to 1/n. Instead of doubling, you need one extra disk for a set of disks you are trying to protect. Okay, rather than twice as many disks. So 1/n seems like a much better price to pay than twice. Okay, if you have 5 disks, you can buy one more. And then if any of the 5 disks fails, you can use the 6th disk parity information stored there to reconstruct. Okay? So this is basically RAID. Okay, this is actually RAID 4, not RAID 5 as is shown here. Okay? The problem with RAID 4 is that this disk that is showing all the parity blocks becomes a bottleneck. The reason it becomes a bottleneck is anytime you write to any of these other 4 disks, you always have to update the parity block. Because whenever you update these blocks, you have to rerun the XOR and write to it. So the write load on the parity disk is the sum of the write loads on all these other disks. Because if there are 5 writes here, 5 writes here, 5 writes here, and 5 writes here, it will be 20 writes here. Because for each of those writes, you have to reconstruct the parity. So basically, the parity block is parity disk is going to see a much higher load than the other disks. Okay? So what RAID 5 does is rather than storing the parity on the separate disk, it spreads the parity. So that's basically shown here. Where rather than having a designated parity, basically store for different block groups, you store the parity on different disks. So you just spread it. Rather than having all the parity here, for blocks D0, D1, D2, D3, the parity block is stored there. For the next 4 blocks, you put the parity here and here. Okay, so this basically distributes the load of updating the parity across all the disks. So if you take any row, if you try to write to a block on any of that row, you also have to update the parity. So if you write to this one, you will have to update the parity here. If you write to this block, that parity information is updated here. So the parity writes get spread across all the disks. It allows you better performance. Okay, so this is RAID 5. Okay, this what I showed here is RAID 4, okay, where it's the same concept. They're still doing XOR. In RAID 4, all the parity blocks are stored on one disk. In RAID 5, they are actually spread across all the disks. Yes, question.
Can RAID 5 deal with 2 failures in the same row or same column?
Can RAID 5 deal with 2 failures? So all of these RAID arrays can deal with 1 failure per parity. If 2 disks fail simultaneously, you will have data loss. Then you have to go to tape backups and reconstruct. Because if this disk fails, okay, that's a disk actually, the column is a disk, then you can use the remainder to reconstruct. So all RAID levels will support 1. Okay, if you need K disk failures, you have to use more complicated schemes than RAID 5.
But if in this case, for example, you disk 20 and 21 fail, then
these are not disks; these are data blocks.
Okay.
Right. So yes, if there are disks, then you could have each parity group. You can support 1 disk fail. Right. So if you have, let's say, 20 disks, and you construct parity groups of 5 disks each. Right. So there is data, parity, parity. Within each group, you can have 1 disk fail. Because these are independent disks as far as RAID is, independent disk groups as far as RAID is concerned. But within a group of disks that are protected by 1 parity, you can only have 1 disk failure. Okay? So that's RAID. Now XFS basically uses RAID. This is why we went into RAID here. Okay, so what XFS does is it allows you to use disks on multiple machines, so you can spread your data across multiple disks on multiple machines. It constructs extra parity information, so if any machine or a disk goes down, your files are still intact. But you can exploit the parallelism that RAID allows you to get. You can get load balancing and so on. Okay? All right, so we are going to stop here today, and